Hello. So thanks for having me. I want to tell you the incredible work that the three teams you see on the screen here. We had the Voyager flight team and Anomaly team that helped us resolve the anomaly that happened on the flight data subsystem, and the Deep Space Network, which is the set of antennas we use to track our spacecraft. The biggest question you may have is, what's a mission assurance manager? So I have the best job in the whole world. Whenever anything goes wrong with an instrument or a spacecraft, I get to jump in and help solve the problem. And additionally, I'm kind of the independent reviewer. You can all imagine back when you were younger, you'd get together with your friends and you have this great idea and it would go terribly wrong. Well, that happens to engineers and professionals at all levels. And so that's my job, is to be the adult in the room and make sure we don't have issues. So to get started, I want to tell you a little bit about the mission so you understand why it's so important to us. And it is very important to us. So the Voyagers launched in 1977, and they were designed to explore the outer planets, specifically Jupiter and Saturn. Of course, they got to all four of them, Voyager 2 doing Uranus and Neptune. And that changed the way we thought about the solar system, utterly changed planetary science. After that, in the 1990s, we became a heliospheric mission. The heliosphere is a magnetic bubble that surrounds the sun, and we're in the heliosphere. It's actually very far out, even beyond planets' orbits. And the idea here was that Voyager would move out beyond these planets, sample the outer heliosphere, and then perhaps make it to interstellar space, because nobody knew there was a heliosphere boundary. Nobody knew how far it was. And so that was our new goal in 1990. Today, we've crossed that boundary, as you'll see, and we're actually in interstellar space. And I think this may be our most important data set that we ever collect, because nobody's going to be here again for decades, perhaps longer. These two spacecraft are deep in interstellar space, giving us information that's critically important. Why? Because, as you can see in the upper corner there, other stars have heliospheres as well. They're called astrospheres. So an astronomer can collect those photons and make an interpretation of what they're seeing, but it's really valuable to have the actual understanding of what that interstellar space might be like that those shock waves are interacting with. So it gives astronomers ground truth in terms of interpreting things like this. The other thing you can see here is that this is some data from one of our instruments. This is the plasma wave subsystem. What it does is it collects electromagnetic information, frequencies, against time, which we heard about earlier today. The PWS actually collects plasma waves. Plasmas are ions and electrons that are embedded in a magnetic field. When that situation happens, those particles will exhibit wave-like characteristics. So this instrument's designed to find those. All these dark splotches are actually what happens when a coronal mass ejection, the things that cause auroras on Earth, those propagate out for years, and when they hit the heliosphere, they actually ring into interstellar space. So Voyager was hearing the eruptions from the sun even outside the heliopause, which was very cool. Nobody really expected that. And you can see this a very thin line. There's a thin line that goes out. That thin line represents the primary plasma frequency, and that gives us density. So this is just one example of the amazing science that these instruments are still providing. Oh, excuse me. So this is a map of essentially where we were and where we are. This is astronomical units on the x-axis on the bottom. Astronomical unit is the distance between the Earth and the sun, or about 8 light minutes. You can see we're well out there, out from the sun. And this is the ecliptic latitude. In other words, how far north and south we are. If you look down at the tiles, you can imagine one of those is an AU. Voyager 1 is about as far away as this patio is across. So, and the distance between Earth and Mars is about that far. So you can see the Voyagers are extremely far away. Oh, actually, you'll see the blue boundary there is also where we crossed into the interstellar space. So it was much further out than most astronomers thought. So these are our instruments. We have a magnetometer. We have the plasma wave subsystem. They're mounted. They use these antennas. The magnetometers are on a boom to keep them away from the spacecraft. The PWS uses these whip antennas. This is a 13-meter boom. So these are not little spacecraft. This is a 3-meter across high gain antenna. And then we have some particle instruments. We have the cosmic ray subsystem, looking at high energy particles, and then a couple of plasma instruments. So those are our spacecraft and the instruments that are still active. So let's talk about our spacecraft status. So we are 15 billion miles away for Voyager 1. I'm going to talk mostly about Voyager 1 because that's what we're here to talk about. Our light time is 22 and a half hours one way. In other words, that's how long it takes us to get a command to our spacecraft. To get a round-trip response, it's 45 hours. So basically, we get contact with our spacecraft after we do something 2 days later. This diagram in the upper corner there shows you Voyager 1 and Voyager 2 crossing outside the heliopause. It's another graphic. I like it because it shows that we're actually moving out through the nose of the heliopause. In other words, just by dumb luck, we ended up leaving the solar system in the direction the sun was going. So the Voyagers are no longer gravitationally bound to the sun. They're actually orbiting the center of the galaxy, and they have a 230 million year period. So they're moving about 3 AU per year faster than the solar system. So imagine a candle. You can see the light from it. You can feel the heat. So all of that energy, if you collect it, then take that and divide it by 6. So 1/6 of the candle. That's 13 watts of energy. So a 70-meter station, the large dish over on the far right, that station, 70 meters across, can detect that signal and pull 160 bits per second out of it. 3 34-meter stations that we array together, they can also perform that feed. So that's essentially how we collect data. Their spacecraft are always broadcasting. We can track it as often we can get these antennas. We can actually go up to 1.2 kilobits per second, and that's how we get that data I showed you earlier. It's recorded on our fancy digital tape crack recorder. It's an 8-track, and it still works great. That data comes down only when we can array all of the stations. So this picture happened earlier this year. This is the first time we arrayed all 6 antennas. We usually have only 5 in the array. So we're working to try and get more and more antennas because we're getting out near the limit of this 1.2 kilobits per second. Excuse me. We don't have a safe mode. Many spacecraft play it safe. When something goes wrong, they kind of shut things down and stop doing things. Voyager 1 just resets its processors, picks up the pieces, and goes. It has very robust fall protection, very aggressive. We have 94 years of experience with our flight systems between the 2 spacecraft. We have about 12 people working on our spacecraft now. So many of them are part-time. That's a lot of spacecraft for very few amount of people. And then our big problem that we're dealing with is power and thermal these days. So we launched with enough plutonium to power the spacecraft. It has a half-life of about 88 years. This is a picture of the fuel clads. When they're fresh, they glow red hot. They're embedded in little cans that stick off Voyager, and there's thermocouples around them. They generate electricity based on the heat difference between the interior and the exterior. We're down to about as much power as a box fan or a rice cooker at this point for those big spacecraft, which is pretty incredible. We also just started operating them with unregulated voltages because we realized we could go off the voltage regulator and keep our instruments powered, which is the reason we're there. And that was kind of a scary moment for us, but it worked well. So far, so good. Generally, we have to take action within a year or less all the time because of our power and thermal constraints. The less power we have, of course, we risk undervolting our spacecraft, and power is also dissipated, so we have thermal issues. We may freeze our roll lines. We'll talk about that a little more. This is a functional block diagram of our spacecraft. You can see Voyager 1 looks pretty darn good. Red is things that are failed, and black are things that are powered off because of power. And then we have a few gold items that are just degraded subsystems. So I think we all wish our appliances worked this well after 47 years. I'll point out this right here. This is the flight data subsystem. We're going to be talking a lot about that. You'll notice there's a very thin line going down into the telemetry modulation unit and then down into the radio subsystem down there. So this is the path we're going to talk about, the path from the flight data computer to the telemetry modulation unit to the radio. Just quickly, speaking of things that are wrong, to keep our spacecraft operating, we have to make changes all the time, and it's getting more and more frequent. Back in the early part of the last decade, it was not a big deal. We could have things happen occasionally that we had to adjust to. More and more now, we're having to take steps to either keep from losing an instrument, avoid degradation, or actually prevent the loss of our spacecraft. So it's getting tougher to fly these with our small team. All right, this is what you guys came to hear, computers in the Anomaly. So we have 3 very cool computers on the Voyager spacecraft, and there are 2 of each type for redundancy. These are humanity's oldest continuously operating computers. So I think it's important to remember that as you hear about them. These are the first reprogrammable deep space flight computers. They operate without microprocessors, and each has its own unique JPL-constructed assembly language. So the CCS is basically responsible for issuing commands to the spacecraft. It's a Viking machine, essentially. The Viking landers and orbiters used a computer of this type, and it's an 18-bit interrupt-driven processor constructed out of transistors. It's TTL logic. We actually use some RC logic on some of our subsystems, but this is a fancy TTL machine, and it has 4,000 words of plated wire memory. If you don't know what that is, you can look it up in the internet, but it reminds you of Rebecca's talk and the weaving. It's essentially a set of wires, and you store data on them by putting a small magnetic field into the wires, and it works great after all these years. Our attitude control subsystem, it is used to control the attitude and pointing of our spacecraft. It's a very similar machine. It has an extra board that they use to make sure that there was enough speed to manage the attitude of the spacecraft. These two are basically alike. Voyager, on the command computer system, we actually use both processors because we're short on memory. So finally, the one that matters to us is over on the far side. That's the FDS. So this was added because during the planning for the mission, they realized that when Voyager flew through a planetary system, it was going to overwhelm the spacecraft data system. All this data coming in under a day, essentially. They didn't think these computers could handle it, so they built a CMOS machine, and it has 8,000 words of memory. And this was put on board basically to make sure that we could process all that data. This is a very important computer for us because it basically commands the instruments. It collects and formats all of our science and engineering telemetry, and it provides all of our timing information. So, what happened and how did we figure it out? So back in November of last year, we had a normal pass come up, but we had no telemetry. So telemetry is basically processed by looking for a frame marker, saying this is a packet of data, and we're going to decode it and look at what it says. We were not getting those frame markers. And the only good thing was we had a carrier signal, otherwise we would have been really scared. So we could see the carrier, but it was not being modulated. So our deep space tracking network, all those antennas, they worked for several days, and they determined that we were seeing a constant streams of 0 and 1 symbols. And there were no telemetry frame markers whatsoever. So the result here was that we had no visibility on our spacecraft. Voyager will drift back and forth based on sun position, and we can see that slight signal variation from over a few hours. We could see that our radio frequencies were per predict, and we could see in the next few days, we could command our spacecraft, but that was it. Somebody on our team pointed out this is kind of like having your monitor broken and having to find out where your cursor is to fix the monitor. So not a very good situation for us. So we formed an Anomaly team. This is about another dozen people that were brought in who are specialists in various disciplines to help us out, which is kind of the way JPL does these things. Mm-hmm. So initially, we realized it had to be the FDS, the TMU, or the radio frequency subsystem after a little work. And we changed the frequency. This is an example by commanding the TMU and the RFS, but occasionally it didn't work, which was puzzling. We also had what's called the open loop recorder, which is essentially using the DSN instead of collect data like a radio telescope. And what happened was we could see that we were getting these modulations, which told us the clock signal was working because the speed was about right. So we knew that pieces were working across this set of 3 subsystems, but we weren't sure what was wrong yet. So we pretty much focused on the FDS based on the fact that we were getting these kinds of transitions, and the FDS wasn't doing much in response to our commands. So our top priority was to figure out what the FDS was and how it worked, because unfortunately, the person who was the real expert had retired decades ago, and the person who was their fill-in, their backup, had retired 2 years ago. So it was the worst place it could have hit us. So these are some examples of some of the documentation we dug up on the FDS, and I hope you guys can see them. That's good, because we couldn't read those. So they're all handwritten. The one up in the upper left has got some handwriting. These are very dim circuit diagrams, and these are handwritten timelines for how to change FDS processors. So this was, we were lucky to find these. Some things we couldn't find. A lot of it was like this that had been scanned. And frequently, these sources were contradictory, ambiguous. Why? Because we changed the way the spacecraft worked with every planetary encounter and entering the VIM and when things broke. So there was a lot of opportunity for ambiguity to arise in the documents over the course of 50 years. This is my favorite example. So this is a page out of an important FDS document. The change bar on the far side indicates it's a change, but somebody went in and made the very cryptic circle the sentence and cross it out. And I have no idea to this day what it means. I have no idea. Maybe it was important. Maybe they crossed it out because they thought crossing out was important. I'm not sure. So there was other cases like this. So we were even so confused in some cases, we weren't sure if we were sending data to the FDS, should it be least significant bit first or most significant bit first? We had that level of uncertainty. So the only thing we could do is dig in and research more and debate. So we had a lot of debates between our flight team and the Tidra team trying to figure out what the best thing to do. But ultimately, we just had to kind of suck it up and guess at some point. And we made the right guesses, which is good. So let me go a little deeper into the FDS so you can understand what we were dealing with. At the top, I'm just going to take this out. At the top, we have memory A. Memory B failed back in 1981. This is the processor. The processor runs the flight software that's embedded on memory. This is, I can't read this. This is how you command the FDS. This is the state vector control unit, which basically manages the redundant units you see here. So if you want to change redundancy, you use this box. This is our oscillator and timing change. This is engineering I/O, science I/O, tape recorder I/O, modulation I/O, and then our encoders. And then we have triply redundant power supplies because this is volatile memory. So a lot of things to look at there. So what we had to do was pick what was most likely to be causing the problem we were seeing and balance that against what was the most risky thing we could, or the least risky thing we could be doing. Some of these we didn't want to play with because we just did not want to switch those components because of the risk involved. So it was always a balancing act. The other thing that happened was this kind of fell into a weekly schedule because we had to wait 2 days for our downlinks. So basically what we'd do is what you see there. We'd observe, we'd design our next tests, we'd build the commands, radiate them, wait 2 days, and then observe the results. So this really was playing 20 questions with the spacecraft. What happened was we came up with this set of things we were going to do, and each one represented a risk-benefit trade. If any of these had come out positively, we would have stopped, right? Because we would have had an answer for what it was. This is like playing 20 questions and always getting no for your answer, no matter what we tried. The only good thing was it let us knock out things that it would not be. So if we swapped out the oscillator and timing chain, we would say, well, it's not that, obviously, and hope that we hadn't screwed something else up on the instrument. So this is a fishbone fault tree. You don't have to read it, don't worry. The important thing is that the brown things are things that we ruled out. And across the top, we have mission operations issues, basically ground stuff. We have safing algorithms on the spacecraft that might have tried to change a configuration. We have a lot of telecom stuff. And then at the bottom, we have all the FDS pieces. We knocked all these out without any telemetry by debate or by trying something like that. This is the FDS in the same type of a diagram. So again, everything brown has been eliminated. And you can see at the top, we took out the MDS. We took out the state vector control and some of the other IOs there on the side. At the bottom, we took out state vector control and timing. We took out commanding and the power in the next to last. And over in the far side, we took out the radio stuff. Again, this was either debate on the ground or trying to swap a component and seeing if we fixed the problem or not. So without telemetry, this is pretty darn good. And you can see we were left with basically just the FDS memory or the flight software. And the processor potentially was there, but we were too scared to touch the processor. So we just kind of said, you know, it's probably working because we're getting timing signals out. So that took us 3 months. And then we arrived at this. The FDS is broken. So we had narrowed it down to that, and we finally figured out why our telecom commands weren't working some of the time. It turns out that the team had built some of those as contingency commands using something called seconds mode, which uses the clock to trigger the commands. Most of the time, we use frame mode. So it turns out that only the framed commands were the ones that weren't working. So this told us, even though we'd forgotten this fact, we figured it out, and it told us that the FDS wasn't giving us frames. So this really put the nail in the coffin that we understood what the issue was. So I'm going to put a couple of names out here. David Cummings at JPL was kind of one of the heroes. Armin Arslanian was the other. David figured out how the FTS code worked because nobody knew how to do it. We have data modes. So data mode is just a different speed of data return. It's like a different modem setting, essentially. So we had 10 different modes, only 4 of those used today. And the idea behind them is they each collect, package, and route data from the FTS to the TMU and then the antenna. And that's the way you work. If you have to, you want a different mode to play back data from the tape recorder versus sending the real-time data versus just sending engineering data. So each of those modes can be thought of as a program, or at least that's how David thought of them. And the problem was we couldn't start or change these programs. Now, underneath those data mode programs, there's the p-tables, and these are code groupings of subroutines that are useful. They're collected. They tend to have the same similar functions, but they're slightly different algorithms. And then under the p-tables, there's yet another layer of code. So a given data mode might use code from different p-tables, and what we really had to do is get our 4 data mode reestablished. So David asked the key question: if code execution was somehow stuck in a p-table, how could we unstick it? And we thought that was the most likely case because commands just weren't having an impact. So it turns out there's 2 variables: mode, which is what you command from the ground, and C mode, which the software sets. And these determine what data mode you're in. And these just flat weren't working, we thought. So we decided to use hardware pokes. Instead of using a nice, safe method where you tell the processor, please write this data to this location, we're just saying, here's some data, put it in that address. And these are dangerous. We lost Viking 1, we lost Mars Global Surveyor to hardware pokes. So we don't like to use them. We'd never used them in Voyager, but in this case, we deemed it the safest way to proceed. So we built 20 pokes, so both variables for each of the 10 modes. And we uplinked that on March 1st, and it didn't look very promising. But the DSN was using the OLR, and this is what they saw. This is residual subcarrier plot on the bottom on the far side there. And where the 2 lines are very fixed, that's our dial tone, right? That's the 0s and 1s as it looks in this type of plot. You can see that when we sent the other, set some of the variables, we got a response, which was the first time we'd seen the FTS do anything in 4 months. So this was pretty exciting. We left it in that one you can see there at the end where it was sending something down. And this told us the processor responded, number 1. It told us memory was sound, and it told us that this was likely a memory corruption. Now, since we weren't producing telemetry markers, we couldn't read this as telemetry. This is just stuff coming down. So the DSN, it's worth a paper in itself. The DSN figured out this amazing way to decode this data and give us what the data represented. And it turns out it represented something really cool. This was an accidental memory dump. Unbelievably, so the processor, we left it in that mode. Somehow it's a direct memory access machine. Somehow it just said, I'm going to read memory. And it was sending us memory dump completely free. So we basically could say the whole memory, and we noticed immediately that there were 256 contiguous words, 1400 to 14FF, that were corrupted or had the potential to be corrupted. And these were all, unfortunately, in that layer of code under the p-tables. So these are routines that are used by every piece of the FDS, basically. And then additionally, one of our engineers determined the next day that this was a single RAM chip in the FTS that is responsible for the 5th bit in each address location. So we understood what was going on. So this is kind of cool. I got permission to actually show you assembly. This is the address, then this is the actual code that's supposed to be there. If the word doesn't have yellow, then it should have 1 in the 5th bit. But if it's supposed to be 0, you can see everything's off by a bit. These are the labels in the assembly. This is the actual opcodes. It looks kind of like 8085 processor. And then this is the data associated with it, and then the comments. So that's what assembly looks like for the FTS on Voyager. And each computer has a different assembly language. So now the hard part, how do you fix that? It took us 3 months to figure out what was wrong. So we had 3 priorities because we didn't have telemetry, we didn't have any memory. 1 was demonstrate we could control the processor again. 2 was get engineering back because that would tell us our spacecraft was healthy. And finally, we don't have a mission if we can't get science back. So the real issue here was the 1990s memory constraint. They loaded up this special version. It was code that just went everywhere because you have those layers of code, and they wanted to reuse everything. With only 8,000 words, you reuse every snippet of code you can. So the code just jumped constantly all over the place. Additionally, Our flight team had never built a load this big, and this was a new process using these hardware pokes. So our flight team had to do a lot of extra work too. So earlier, when all that investigative work was going on, we found some object code. And it turned out this was a program called min-sim-rot that had not been used in 35 years. And it actually does this small amount of framed clock telemetry, sending it back to the ground. And it's framed, which was exciting for us. And we thought that would be our good Hello World program. And additionally, they took min-sim-rot and they morphed it. This is where Armin began to help out. They morphed it into a program that would use that same framing, but give us an MRO. So in prep, we told the FDS to not generate frames because we didn't want the processor to wake up and begin issuing commanding that was on board and loaded on our spacecraft. So we turned off frames, we uplinked and linked min-sim-rot. That means we loaded the program when we put the pointer at 0 where min-sim-rot loads. That's how we link. And it actually worked. We got telemetry using this. We had a custom tool that they developed for us again. And then we sent min-MRO the next week, and that worked as well. So far, so good. We had the processor under control. Next, we had to repair the codes. This is 256 instructions that had to be relocated. We had to preserve the behavior, of course, to get our data back. But timing was key because anytime we added a step to do these extra jumps, it would play with the timing of the program, which could kill us. So we understood we had to be super careful with the timing. So the only benefit we had was that we were cannibalizing one of these obsolete data modes we had. Now, the challenges these guys faced were incredible. We didn't know that we had the right instruction set. I showed you in the instruction set there. We didn't know that was the one that was used to build the software back when there was an assembler. We didn't know that the source code version was the same as what was running on board the spacecraft. We had a listing of the code, but it was a Microsoft Word document that was optical character recognition scanned. So we didn't know if there were errors in it. We have no assembler, so they're just playing with bits. There's no simulator, and there's no test bed. So there were a few challenges. So basically, this was bare-knuckle binary manipulation. And they had to think of all the problems. I'm sure you guys are far better than I am at thinking of the problems associated with playing with memory like this. You could overwrite something. You can fail to recognize jumps. How do you debug it in flight on a flying spacecraft? And how do you know you're not missing something in those instruction sets and codes? And the list goes on and on. So what they did is they took every possible thing that could go wrong. They made a list, and then they iterated their code adjustments with that list with multiple people. And that was essentially how they came up with these patches. And we said that was okay because we were effectively no telemetry without that. And frankly, how bad could things get worse than they were? So we uploaded this and linked it on April 20th. And this was a big day. We got telemetry coming down for the first time. This is Armin in the blue and David in the green. And then this is our flight team, our tiny little flight team celebrating. So that was a good day. But we weren't done yet. So now we have to get the science back. And we were worried because it took a lot of code to get one mode back. Now we have 3. It turns out it wasn't that bad. The code reuse was pretty amenable to what they'd done. But we did have some other problems. Again, we were out of space. We'd used it all up. The engineering high rate memory that we were cannibalizing, it was gone. So we found an old memo from the 1980s that mentioned free memory. We looked at the memory readouts and it looked like it was just not being used. So we assumed it was free and went with that. This was an upper memory and it wasn't in write protected region of memory, which was a concern because we'd like it to be write protected. But if we went to lower memory, it takes an extra step to go between high and low memory. So we were worried about the timing implications again. So we ate the risk that we were writing to unwrite protected memory. And we patched it on May 18th and it worked as well. So I want to kind of highlight that one because I keep saying this little statement like it's really easy. These guys did 4 patches, we uplinked them. But I want to show you just how hard it was what they did. So this is a map along the bottom. It's 0 to 255 words, trust me. And then the next row up that's kind of slanted, you'll just keep counting up, right? These are addresses incrementing along there. This is upper memory, 4,000 to 8,000. So this is essentially a memory map in Excel. This blue line going across, this is the failed chip. So all of these locations were trashed. We didn't need the little piece that's called copy in the middle there, but all the rest of this had to be relocated. You can see that they took some of the subroutines and they broke them into pieces. They stuffed them anywhere they could find any space, all over the memory. This is all upper memory. They put in 14 different specific relocations of code in this case to recover the functionality that was lost in the blue line. Additionally, this is now from 0 to 8,000 addresses and 100 addresses across. These are all of the new and modified instructions that they had to do. They had to change to reference this relocated code. Again, no assembler, no testbed, no simulator. These guys were awesome. Then finally, we had to restore our spacecraft and instruments. So we got our frames turned back on. We had to resync our clocks. We got the autonomous sequencing roughly going. We're still playing with that because things got pretty screwed up. And 3 of the 4 instruments had stopped working properly because the FDS is kind of their caretaker. And one of them has this little motor. The upper half of this instrument rotates 180 degrees in 8 discrete steps every 2 minutes or so. It's stepped over 8 million times in flight. It got stuck during this downtime. So we reinitialized the instrument, and it looked pretty bad for a while. And then little by little, it broke itself free and began to work again, which was really good news for us. So basically, at the end of May, we were back to nominal operations. And then we had 2 data modes for the PWS, the playback and record, and those were confirmed in July. And that's how you fix your 47-year-old computer from 15 billion miles away. It was pretty cool. And just so you know, I didn't do that. That was David and Armin. They were amazing. So I'm not going to go over this whole slide because some of this is internal, but I just gave this talk Thursday for the first time, so you guys are the first people outside of JPL to hear it. I think the Voyagers give it this beautiful balance in their software between operational flexibility balanced against understandability and intrinsic robustness. In other words, Voyager software is understandable, it can recover from almost anything, but it's also flexible, and that's a hard balance. I think nowadays, most of the spacecraft I work on, you can't tell what the software is going to do because you have competing algorithms, you have so many possible triggers for call to actions that you can't anticipate them in simulators. So I've seen cases where we get algorithms fighting it out over battery control or something like that. And you just can't figure out, even the experts can't figure out what they're doing. We could figure out what Voyager was doing even without telemetry. I think the negative that really hurt us was our spacecraft have been healthy for decades, and that certainly contributes to a loss of knowledge. And then I think we talked a little bit about fabric and maintaining data. You guys thought lost and inaccessible documentation. Voyager's been through so many media transitions, right? Paper, through scanning, through CD disks, through tape drives, we used paper tape and cards at the beginning. Some of our ground software was basically on a Unix system, but it's emulating a water-cooled UNIVAC from the 1970s. All this stuff is evolving constantly, and over a 50-year mission, we didn't have the money to maintain it. So we got into the situation where the documentation was bad. So I agree that's a really difficult problem, and we need to do a little better with that. But we do have some final goals. We're dealing with some of these issues we had because we want to get out to around 200 AU, which would be in, 2035. I don't know if we will get there. So the gray boxes are years. The gold numbers underneath them are the actual AUs we're away. And these bars with LECP, CRS, MEG, and PWS, that's when the instruments get turned off. They've already been on about 6 years longer than we thought we would have to turn them off because of the changes we've made. These little colored boxes, if I take one of those away, this timeline shrinks by that amount. These are all steps that we take to increase the timeline. So our goal is to keep them alive until 2030s, something like that. But you can see that I've got an estimated survival probability there in the light pink. The probability of us making beyond 2028 begins to drop pretty quickly. So we've got at least 4 or 5 more years in them, I think. We're also having some thruster issues that may be the end. We're going to do a thruster branch swap in the next 2 weeks, so keep your fingers crossed. And then last, we are an inspiration mission. This really taught us that we matter to and inspire people around the world. Our project manager, Susie Dodd, calls these humanities spacecraft because people do care about them. We had universally positive and supportive media coverage during the Anomaly, which is pretty rare these days for any event. We had 90 significant media hits, hundreds of internet stories. On our website, it was the big story of the year, and we had social media mentions and benchmarks way above average. But best of all, we get really cool fan mail. So, danke.